But again, I wanted to start out by saying, what are we focused on today? We're focused on metal additive manufacturing, and specifically the metal laser powder bed process. All of our tools today are set up, pre-configured for this process. Does that mean our solvers can only do this process in these materials? No. We could actually configure them to do just about any process and just about any material. But when you buy the tool as it stands today, it's pre-configured for the metal laser powder bed process, which is the main one that most people are spending a lot of time and money trying to optimize for their production needs. And so in the future, we're going to then come up with configurations of this tool that are configured for all the various processes and materials of interest to our customer. So we think about, how did additive manufacturing start to become this big thing? I think we point back to two things. One was an Economist article that said, print me a Stradivarius. And all of a sudden, everybody thought, hey, if I could print anything. And in there, they talked about printing aircraft components and other stuff as a future potential. A lot of companies said, hey, we need to look into this. And people started dumping a ton of investment in there. And then GE, at the same time, a few years later, published this kind of case study where they were developing a fuel nozzle with additive manufacturing, and they talked about how generating this one geometry that we see here has all kinds of internal geometry there that allows it to be much lighter in weight, much more fuel efficient, and it's all a single component instead of an assembly of about a dozen components in order to create this fuel nozzle. And this became public, and now engineers started to take notice and say, hey, we need to do this too. Other companies need. Now, a lot of your companies out here, I know, were also working at the same time and we had similar successes, but maybe weren't out there publicizing them as much. But I would say this really generated the hype in the engineering community. And so people went out and started buying these $1 million machines and trying to build similar components. As people jumped into this hype and started buying the machines, they started saying, hey, oh my goodness, this is costing us a fortune to try to qualify all of these processes with trial and error. And one of the main reasons, it comes back to this main drawback of metal additive manufacturing, which is that parts distort as they're built. So you're melting a metal, it shrinks, right? You have accumulation of that shrinkage with little tiny micro welds. In fact, millions or billions of little scan vectors are scanning. So you need to put supports on these parts to rigidly attach them to the base plate. So this is not necessarily true of polymers. You don't necessarily have to always support them quite as much. But in metals, we have to rigidly support the part to the base plate. So, and when you cut that off, it's going to distort. So here's an example geometry right here. So this part is a bike stem. And so if we take a look at this part, basically, this hole here goes to the down to your tire. This hole here and this hole here are where you're supposed to attach the shocks. So because this is for a mountain bike, and then your handlebars go across here and are clamped onto the top. So it's a topologically optimized bike stem. And so again, it's a relatively simple geometry. But what happens when you cut off these supports is it bends. And I don't know if you can see from back there, but if I push on this, you'll see that it's bent. And so it no longer lays flat. It basically will rock. And so this is a classic problem of what happens in additive manufacturing. You'll build something with tight tolerances, or you'll specify tight tolerances. The whole thing will warp, and then you have to figure out, how do I keep it from warping? Do I heat treat it before I cut it off? Do I add machining stock and allowances? And what happens if I change the orientation of this part? It'll warp differently, right? And so now, all of a sudden, a simple geometry has become a huge engineering problem of how do I actually make this successfully? So one of the things we actually do with our Ansys additive print product, just a little preview, is we have a button you can push that says Distortion Compensate. So if you predict a distortion that it's going to warp up, we have a simple reverse distortion algorithm. It basically distorts it in the opposite direction. And then when you print it and cut it off, it goes back to the correct geometry. If you think about the cost of failure in additive, if you have a build that bends up as you're building, then if it bends up too much, you're spreading more powder and it's going to crash into that part because it'll actually deform out of the powder bed. And so whether you crash into the part or whether the part is just outside of conformance, right? If you think about metal additive manufacturing, each failure is usually thousands of dollars. And this is an actual bucket of parts next to one of our customers' machines. This is where they throw their failed parts. And this is common for a lot of places that are trying to generate a lot of different designs and test them out. And so this was the cost of failure that we set out to try to help our customers avoid. So let me talk about a simple case study that one of our customers did, Croft Filters in the United Kingdom. And it builds nice and accurately. The blue color here indicates a predicted build that doesn't have much distortion. But what you find is as you put this top on it, then you're going to start to build up compressive stresses in that top ring, and it's causing that to bulge. And when you complete that, now we've got a part that bulges and is outside spec. It will no longer assemble into the collar that it was supposed to assemble into. And this customer actually spent 6 months. This is a very sophisticated additive manufacturing user. A lot of successes with additive manufacturing. They spent 6 months adding stiffening ribs and changing the lattice structure slightly to see if they could reduce that distortion. They hired an intern and just gave him our tool and said, try it. And in his first week as an intern, tried it out, ran some distortion compensation, built it, and basically had this exact result. So in one day, a new person was able to set up the build, simulate it in another day, check the results a day after, print it the next day. Basically, distortion compensate, reverse distortion compensate, so when they built it, it swelled to the correct geometry. So once again, what we're finding is as these sort of simple insights that before you had to, through trial and error, over and over, see what's going to happen, and then try to counteract it. If we can predict what's going to happen ahead of time and use some simple, compensation tools, that people are starting to see some success in a much easier way. And when you think about additive manufacturing, each machine manufacturer uses a different scan pattern logic. That means they have a different arrangement of how they scan or melt that part with that laser. And so some of them use a checkerboard pattern, which is what we're showing here, but most of them actually use a stripe pattern. So they basically create a stripe and then scan one stripe and then scan the next stripe and scan the next stripe. And so if you think about a different scan pattern, as engineers we know, if you put in a different laser scan pattern, we're going to have a different thermal or temperature history. And so the pattern of heat is going to change, and that is going to result in different strain magnitudes and different defect distributions and different microstructures and in different mechanical properties. It's a completely new architecture for doing this. It doesn't rely on any pre-existing simulation tool set. It basically is a combination of finite element, but also of eigen mathematics. It also takes into account what we call periodicity. And periodicity, if you think about all these scan vectors, all of these scan vectors typically have the same laser being used for it, the same laser power, and the same scan speed. So the energy input side of the equation is very repeatable, but each scan vector, the cooling side is slightly different because it'll have a different history leading up to when that happens. So mathematically, we've decomposed the heating and cooling into different modes, and we can solve those quickly and then reconstitute them. And now the beauty of doing all this is that now Ansys has developed this ability to predict this thermal history at that melt pool scale, but for full-scale components. So what are we predicting here? We're not predicting, it's not a fluids analysis, it's a thermal analysis, but that analysis takes into account the phase of the material, the state of the material, and the temperature-dependent thermophysical properties of that material. So what are the phases and states? You've got a powder state, you've got a liquid state, you've got a solid state. Within the solid state, you could have alpha and beta phases, or you could have multiple materials even. The solver could handle that as well. And for every material in there, you have to have a whole set of thermophysical properties for every temperature. And so we have this massive lookup table that basically says what are the thermophysical properties for each of these states. And so if you think about the powder, some of the properties are just a scale. If the powder is 50% packing density, then certain properties scale by just that density. But if you're thinking about like thermal conductivity, then thermal conductivity does not scale by packing density. It's actually about 0.1% of the solid thermal conductivity when you're in a powder state that's loosely packed. This is something that's unique about Ansys' solution. No one else has anything like this. All the other solutions you'll find out there, and including Ansys has one of these kind of solutions as well, take a traditional finite element solver and we sort of generalize the temperature or the heat or the strain accumulation and sort of average it and lump it and sort of copy paste that lumped thing. If you're looking at all of our competitors' solutions that use thermal, that's what they do. They copy paste a lumped solution. And so we put this all together into one tool set, and what are we bringing to the market today? So let's say that we take a classic over-designed structure, like what we see up here in this location. And then our tool sets, we have great topological lattice optimization tools that allow you to basically go through and take that geometry and come up with a more optimized geometry. Now again, our traditional Ansys tools will allow you to validate that that geometry will actually perform as you want it to. But now with our new solver technology, one of the things we do is we can generate physics-based supports, and we're spending a lot of time and effort this year to make this better and better. Today what we do is we predict layer by layer how is the stress and strain accumulating, and based upon that we can tell you where do I need supports and where do I not need supports. And we generate an STL file of a support structure that's optimized for that part in that orientation for that machine and that material. As part of this print process simulation, because everywhere in space we're predicting that temperature history, now we can do some really cool things with that. We can tell you, for instance, this little animation on the left, blue is powder, green is solid, red is liquid. You know, we can basically say, how is the state of the material evolving, and where do we have porosity left in the material after we're done? And if we know what the temperature history is, a lot of you who are more material scientists know, hey, it's the temperature history that drives microstructure. So let me show you a couple of the products and a couple of the types of results we can get with this. So when we think about our products, we recognize that we have a couple of different types of customers. You could basically break down in any number of them, but here's a couple of big categories we break them down into. So you have a designer or an operator. This is a person who's usually not a finite element analysis expert, and they don't necessarily want to be a finite element analysis expert. They just need feedback on, if I put this part in my machine, can I build it successfully? Or you know, can I generate supports more easily or do my build setup? And so these are machine operators, designers, who just need practical information about how does their geometry change in the process and how do I set up the build without failing. And then there's another category of people, the engineers and the scientists who want to go much more in depth, predict microstructure, do parametric analyses, try all kinds of what-if scenarios. And so what we're building is a couple of different user environments to try to satisfy both. We're building a nice, simple, standalone additive print feature for the designers and operators, and then we're embedding more and more technology for analysts into, over time, Workbench and Ansys Mechanical, as well as giving you also some standalone methods maybe for the material scientist who doesn't want to become a finite element analysis expert. So the outside package we call Additive Print today. Additive Print is a lightweight standalone application. Again, it's delivered outside of Workbench. It's available in both desktop and cloud. I'm going to give you a demo of the cloud, but the desktop looks exactly the same. We include Space Claim. How many of you have used Space Claim in the room? Looks like about half or 2/3 of you. So why do we include Space Claim with all of our additive products? It's because it's really the best tool on the market today for taking CAD geometry from all kinds of different types of formats and bringing them together and comparing and contrasting and tweaking your STL file and repairing it and all of these things. It's a great tool for that. And so let me show you a brief thing we did 2 weeks ago with one of our partners, Renishaw. Wanted to perform a very simple calibration of our tool, predict and compensate from that simple calibration a complex part that we'd never built before, and they'd never built before, with a very tight deadline, so we couldn't game the system. So there was no opportunity for trial and error. We're just going to do it and show it what it was. And I actually got the results the night before the presentation. Renishaw built a simple geometry. They measured that, sent us measurements of what happened to that little simple geometry. Then we tried to use that as a way of predicting what would happen to a complex part. So we provided 1 week before AMUG the simulations results to Renishaw. They put that into their build schedule, built it, and then the night before the presentation, they measured that build and gave us the results. And so here's the geometry. This is a classic, very difficult to build accurately geometry because it's got a bunch of thin walls, but also some thick to thin transitions. Those are always problems. You've got some internal passageways, and as this curvature is this type of curvature that if you don't support it, it's going to warp all over the place, and typically do that. And so, the material we built it out of Inconel 625. It's about 120 millimeters in each dimension. The blade thickness is about 1.3 millimeters, so relatively thin blades. And so we wanted to see what was going to happen. So anyways, the part that we used to calibrate it was a simple octagon, and we took caliper measurements at the bottom, middle, and top. And so that's what they gave back to us. So all we got from them was the caliper measurements. We ran a few simulations and tuned a single parameter in our simulation. Well, actually, we did two things. One is we took the Renishaw mechanical property database that they published for their Inconel 625 material and pulled the modulus of elasticity and yield strength off of that database, and we put that in the solver. So we changed those two things. And then the third thing we did was calibrate what we call a strain scaling factor. So in this most simple simulation we did, we actually are saying we're accumulating the average amount of strain everywhere. So all we're doing right here is with a single measurement saying, what's the average strain that occurred in this part? And now we say, if that average strain occurred in the complex part, what would happen there? That's really this simple test. And it's our most simple, fastest simulation type. And then we went and predicted this complex part with that simple simulation assumption. And so here's the first set of results. So if we animate layer by layer what's going on with this complex part, we start out blue again is least distortion. The dark red is 1.4 millimeters of distortion. Remember, the blade is 1.3 millimeters in thickness, so we've actually moved the blade more than its entire feature thickness if it gets to that level. And you see that it starts out relatively accurate, but as the blade continues to be built, this lower region distorts more and more and more, and over time goes way outside of any tolerancing you'd have on that blade. And so this simulation, we ran it at 300 micron voxel spacing. That's basically the nodal distances in the solver. We basically just decompose the geometry into little cubes, and voxel is the size of your cube. It solved a total of 2.4 billion degrees of freedom in that amount of time, with the very last time step being 9.6 million degrees of freedom in a single time step. That took 28 hours to solve at that level. And so here's the types of results we got for those 28 hours. We got that. We also compared two different geometries of this blade. And so we have something that we call a blade crash severity. So if something bends up in Z, it can hit the blade, and depending on the design of your blade that's pushing the powder, it may crash or not. So gray means there's a chance of it scraping. Red means it might hit kind of hard. And at this geometry, the little tips of this were showing some scraping. And indeed, they said, yeah, it scraped, but it was not enough of the material was scraping to actually fail the build. They had one design they also tried to build that we did here, where the entire blade was sticking up. You can see that the angle here is much sharper rather than this is sloped up at a much kind of less of an angle. And so this one actually smashed the blade and actually failed. They had to kill this build, and it wouldn't complete. And our simulation also showed the difference between the severity of that. And they said, sure enough, yeah, what was happening over here, you know, that's too much. It killed, but over there, just a tiny bit of the edge, and it was okay. It can kind of bump over top of it and keep building. So we basically went in and said, okay, if we kind of superimpose the distortion, we can see that in red here, it's moving quite a bit in one direction. If we zoom in, let me zoom in somewhere on this part, maybe down here in the bottom, you can see that basically the fin is moving the entire width of that fin out of compliance. So now you're not going to have the same aerodynamics. And indeed, that's how it built. So we went in and did a simple distortion compensation where we reversed the distortion by a factor of 0.75. So that means that if it was going to distort 1 millimeter this way, we went the opposite direction at 0.75 millimeters. And what you find is that in general, most materials you reverse the distortion somewhere around 75 to 85%. And that's going to get you, when it redistorts, it's going to get you about the right level of distortion. Then we measured at a Z height of 30 millimeters and predicted that, hey, indeed, we're going to see, the distorted geometry is now is going to line up pretty well. The distortion compensator should line up pretty well with the design. So we went there, and we measured it. We showed the prediction versus the measured. They were either better than predicted or quite good. But the main conclusion is that just with our most simple simulation type, we had an 80% reduction in distortion. So it was a nice proof of concept, and we've seen a lot of customers do this over and over and over. Most of their geometries I can't share, but this is just one I could kind of share you through. What we're doing now is going back and running this with a lot of our more complex solutions. This didn't do the full thermal solution. In our full thermal solution, every time a location gets reheated, we increase the amount of strain in locations where it gets thermally cycled more. So certain portions would have more strain than others. In this solution, we just applied the average strain everywhere. And so we'll have that all built up into a case study here in the next month or two with the more complex simulation types and see if we could even get better than that 80% reduction. One of the things we also tested was in our 19.1 release, we have a new way of using more HPC packs. And so we ran this at 28 hours with the equivalent of our 19.0 release. In our 19.1 release, using 12 cores, that brought it down to 8 hours. If you want to use even more cores, it's going to bring it down even more. If you run it with larger voxels, then you could run it even much, much faster. That 300 micron voxels was basically maxing out the memory on this part to do it that way. So that's the kind of thing you can do with Ansys Additive Print. Let me just briefly talk about the rest of our suite. We're going to see a couple of simulation examples here in a minute where we're going to walk you through some of the tool itself. But in our Ansys Additive suite, it's all things Ansys Additive. And so it includes a bunch of stuff we're going to do in Workbench, which you're going to see a demo of here in a minute. It includes additive science, which is where we start to say, okay, what can we get out of all of this thermal information that we're predicting? Then additive print, which I just showed you, is all about distortion and geometry changes in the part. But additive science is looking at the details inside the part, like microstructure, porosity, etc. So let me just show you a couple of examples from additive science. I'm not going to walk through in my demo how additive science works, but let me show you some of the output. And then you're going to see output in the demos of Workbench and additive print here after the break. So, whoops, let me back up a second and just say in additive science, there are 4 main things that we're predicting with additive science this year. Melt pool, sizes and shapes. So what's the size of the molten region at different process parameters? Why would you want to do that? Well, it's because if you're trying to develop new process parameter sets, let's say that the default in your machine is for 40 micron layers, and you want to run at 50 micron layers, or you want to run at 30 micron layers, or you want to see if you can run faster on that material, then you need to be able to predict what's going to happen to my melt pool if I go higher power or more laser speed or change the layer thickness. And so what you do is you look at the melt pool predictions, and then you predict what's going to be the porosity when I take that melt pool, basically start to build 3-dimensional patterns of those melt pools to build up a full-scale part. What's going to happen to my porosity? So these first 2 bullets are really about how do I do process parameter development in my part for new types of scan strategies or new materials. And then the last 2 things with additive science that we're putting out, our thermal history prediction. What does that mean? We're predicting what a sensor would see if it was measuring the process. And so we have different sensor types you can output. Why do we do that? Well, one of the reasons is we want to make it possible to start building a digital twin. So you have a physical machine running, and we want to have a digital representation of that machine running in parallel, predicting what you should see happening in the machine if the machine is operating correctly. If they align, now that's a qualification procedure you can use for quality control. So that's why we predict what a thermal history you'd measure. And lastly, we're releasing microstructure prediction, so you can actually get microstructure details. So I'll show you a couple examples of the last two. So one thing we can do is you can pick points in your part. So here's an example. This is a stripe. The blue dot, the green dot represents a laser scanning back and forth within this stripe within a layer. And these little black dots are locations where we put a probe and said if you had an infinitely small thermocouple there, what would it measure? And then basically you have a temperature history that's over there. So that's the sort of thing you can probe different points of your part. Tell me what was the temperature history there? That's more for, material scientists would want to know that sort of stuff if they're thinking about microstructures. But if you're more looking at qualification, you might want to do something like this. You might say, okay, what happens if I have a sensor that's looking through the laser optics and I'm just averaging something that I see through the laser optics? And this is actually a very common sensor type that you get with laser processing. And so within a field of view, the field of view might be 1 millimeter, 2 millimeter, 3 millimeter. I'm averaging something that I'm measuring, like the average temperature or what's the melt pool width that I'm seeing. And we just basically say everywhere the laser went, what was, for instance, in this case, the average temperature within that field of view. And then we paste that as a picture. And you'll see that a lot of the machines out there, EOS, Concept Laser, Renishaw, they all have sensors now that you can buy that do this exact thing. So we're predicting what those sensors would see. And what you see is that layer by layer, that picture changes a ton. And why does it change so much? Because every layer, it's orienting the scan vectors in a different way. And so sometimes we have lots of little tiny scan vectors, just by how it got sliced. Other times we have really long scan vectors. And so this one is actually a relatively cool layer in the way that the scan vectors are aligned. But you'll notice some layers, you would measure some really big hot spots that you're going to see in the sensor. And that's not because this is not measured data, this is predicted data. And so what this shows is the variation people are seeing with these sensors are not the machines out of calibration. It's actually an artifact of this type of scan strategy that is being used. And so over time, we can help people design better scan strategies to even out that temperature profile so that you can have a more repeatable result. And so again, that's how the tools, we're designing them to be used. And so finally, the microstructure. Basically, if you can extract information about the thermal gradients, the cooling rates, the melt pool, etc. Now we have a cellular automata tool that we're introducing with our tool later this year that'll predict that local microstructure. And the first prediction that we're getting you is basically going to predict it in this manner. We're going to basically say, you select a point, and we're going to tell you what the microstructure would be if you cut it in 3 orthogonal planes near that point. And so you got simulated, you got experimental. Now the first thing to notice about this comparison is that the color bars don't represent the same thing. So color here is not meaningful. But what you should look at is pattern in this comparison. So on this face, you have a texture in this direction, and we predicted a similar texture with a similar grain size in that direction. From this face, again, you've got melt pool, you've got this thin region, a larger region, a thin region. And over here, you see the same thing. A thin region, larger region. All of the pattern, the basic grain size and orientations we're predicting are the same. And so in our first release of our microstructure prediction tool, it's basically going to do that. You select a few points. We'll tell you what these patterns will look like, the grain shape and the orientation of the grains on 3 orthogonal planes. But we also have in our architecture the ability to predict your primary and secondary dendrites and your dislocation densities and some other things that we'll be releasing in later releases. So my kind of last slide is, we just wanted to say Ansys is committed to additive manufacturing. We're really committed to this long term. We're investing aggressively in this. We have over 50 people focused on additive right now. We've done a lot of hiring this year, and we're also partnering in the ecosystem, trying to basically say, hey, we can't do this alone. We have to work with the machine manufacturers. We've got to work with the material suppliers, parts producers, universities, research labs, and our customers, of course, to make a successful solution. So, in summary, I think really what I've hoped to illustrate in this quick overview is that advanced simulation for metal additive manufacturing is actually now available. It can predict things like distortion, where you need supports, if you're going to get blade crash failure, what's going to be the microstructure, what should be the sensors you would see in the machine, and more.